Okay, so identifying some phase changes here. Snow on the ground turns to liquid water. Everybody knows that's melting, right? Not going to happen probably for a couple days outside. Is that exothermic, endothermic, or there's no heat transfer there? That is endothermic. We have to put heat into the snow to get it to turn into water. Water in a pan changes to steam. Yeah, vaporization or evaporation or boiling would be another word, but that's not a choice here. And is that exothermic or endothermic? That's also endothermic. We need to put heat into the water to make it steam. Just like we put heat into the snow to make it water.
So I thought about the steam. So the water change from hot water to stone, it will be exothermic.
No, endothermic.
Endothermic?
You have to put energy into the water to make it become steam. All right, this was the rest of these I think were all questions from the book. On a hot sunny day, a metal chair heats up more quickly than a glass of water. What does this tell you about the relative specific heat of each material?
The other materials take the heat, so it will be
yeah.
The materials can shiny and I don't know.
It's not about conduction because this is not talking about electricity. This is talking about heat being absorbed from the sun.
So
specific heat is take longer. Need a big energy for small specific heat.
So something with a high specific heat, like water, requires a lot of energy to raise its temperature. Something with a low specific heat, like metal, requires only a small amount of energy to raise its temperature. So this tells us that water has a much higher specific heat than metal. The same amount of heat is going to both things. For the sun is heating up both things the same amount of heat, but the metal chair gets much hotter because it takes less energy, less heat to raise the temperature a greater amount. Ice cream has 44 grams of carbohydrates, 28 grams of fat, and 8 grams of protein. How much energy in joules does the ice cream contain? So here I have a chart telling you the energy density for carbohydrates, fat, and protein in kilocalories per gram. So we need to just multiply each of those. 44 grams of carbohydrates times 4. Then 28 grams of fat times 9. And 8 grams of protein times 4. Let's see, so 160 plus 16 is 176, right?
Yeah.
Okay. 28.9 is 252, is that right?
Yes.
And then this one is 32. So we add all those up and get 460, right? All right, and that's kcals, but the question asks for joules, so we need to do the conversion. Our conversion is given here, 460 kcals. We want to convert from kcals to joules. Somebody do that one for me.
So 192,464.
Like that?
No, 192,464.
Okay. Maybe I should just do it. Okay.
4640.
Oh, 192, 46, 40. Okay. All right, so like that. It's a lot of joules. Another way we might do is put that in scientific notation. So 1.92 times 10 to the 6th joules. Round it off a little bit. Okay. And then how much energy is required in calories to heat 38 grams of water from 122 degrees C to 246 degrees C? We need to find that change in temperature, the delta T. Which is 124 degrees C. So the heat or the energy is going to be 38 grams times 124 degrees C, excuse me, times 1 calorie per gram degree C. 38 times 124. I suppose I could just do the calculator here.
4712.
All right, so another good quiz, hopefully. Great.
So we can skip like a last one. Yeah, last part. Or one calorie for 1 joule. We can skip. We can skip.
Yeah, it depends what the question says. That question said calories. The previous question said joules. So whatever is asked by the question. So let's move on. Last time we talked about atoms and electrons. And we figured out how many valence electrons a particular atom might have, a particular ion might have. We talked about making ions, so adding electrons or subtracting electrons, and then putting the charge up there, plus or minus however many. Today we're going to focus on putting those things together into compounds, and then we're going to look at some rules for naming those compounds. So we have to know what we're talking about throughout the semester, so we have to know what our compounds are called. So we're going to spend a little time on some naming rules. Remember back from a couple weeks ago, compounds are going to be multiple elements put together. So instead of just looking at one element, we're looking at multiple. And these are ionic compounds, which means these are compounds made out of ions. We're going to look at the other types of compounds, covalent compounds, later. But for now, we're going to focus on ionic compounds. So in an ionic compound, you have a cation, we'll just say like a positive ion, and an anion together to make an overall neutral compound. Like if I had sodium chloride, I'd have a positive sodium ion, a negative chloride ion. I'd put them together, and that compound would be neutral, one of each, the neutral compound. All right. Where it gets a little bit trickier is when the charges don't balance initially, and we have to adjust the number of each ion to account for that. So let's say I had a calcium ion. We can look at the periodic table and see that calcium is in group 2, and therefore would be a 2+ ion. 2 valence electrons that it can lose. And then let's say I want to make a compound from calcium and chloride. Chloride ion is a -1 ion. Everything in column 7 there has 7 valence electrons, so 1 additional valence electron makes it a full shell. And so all of those make 1 minus ions. All right, so I make a compound between calcium and chloride. But if there's a 1-to-1 relationship here, if there's 1 calcium ion for every chloride, 1 chloride for every calcium, that's not neutral overall. Do you see that? We have 2 plus from the calcium, and we have 1 minus from the chloride. So we need to have a different ratio here to make this neutral. We need to have 2 chlorides for every calcium. And I'm going to write the sodium one that we just talked about over here also, just so we have it for comparison. The way that we write the formula, what we call the molecular formula or the empirical formula for this compound, is going to be different for these 2 cases. Sodium chloride, we know, is NaCl. Putting those 2 things together like that assumes there's a 1-to-1 ratio of each of those. For every sodium atom or ion, there's a chloride ion. For every chloride ion, there's a sodium ion. Calcium chloride, we're going to do that a little bit differently. The formula for calcium chloride is CaCl2. That little 2 down there means that for every calcium ion, we need 2 chloride ions in order to balance the charge. Both of those compounds together are neutral overall. They have no charge overall. Let's try another one. What happens if we want to make a compound of sodium and instead of chloride, we're going to use oxide. Oxide is O2 minus. Oxygen's the next row over or column over with 6 valence electrons, which means it wants 2 more to have a full shell. So if we have a sodium ion and an oxide ion, what do we have to do to bring those 2 into balance?
We'll change it to minus.
We can't change charges though; those are just the charges of the ions. We can add more to one or the other. We want it to be all neutral overall.
Add 4.
Add what?
Add 4 O2.
Add 4 O2s. 4 more besides this one. All right, let's try it. So now what's the overall minus charge in that compound? Now it's minus 10, because each of those is minus 2, and now we have 5 of them. So now we have +1 and minus 10. So that's not really solving the problem, but a good idea. What else? That's not really helping us. What could we do?
Same like chloride, we have 2 minus there in chloride, so it's also O has 2 minus. Can we say like natri O2?
So if we said NaO2 like that, that means that we would have another oxide ion. Does that work? Do those charges balance?
No.
They don't, because now we have 4 minus and 1 plus.
We cannot separate.
So what are we going to do?
Can we say like this?
Yeah, so that's going to be the way to do it. We don't need more oxygen, we need more sodium. If we put a second sodium ion there, now the overall positive charge is +2, and the overall negative charge is -2. And in fact, this is how you would go about trying to figure out the compound that's formed from any two given ions. Let's try another one. Let's say I want you to write a formula for lithium sulfide. So we need to figure out what the formulas of those ions are, what their charges are, and then how many of each we need to balance the overall charge. So what's the formula for lithium? So you could look this up on a periodic table if you've got one with a name, but if not, I'll just tell you it's Li. So lithium is Li, and that's number 3. So what should the charge be on that? What charge do you expect lithium to take? Plus how many? Plus 1. Why?
We have code 1A.
Right. So anything in that column has 1 valence electron, and it can lose that valence electron to become plus 1. So all of those elements are likely to make a plus 1 charge. We usually don't write the 1, we just write plus, but that means plus 1. All right, what about sulfide? Sulfide is, the symbol is S, and that is number 16. So what would you expect the charge on sulfide ion to be? Six plus? Minus 2? Minus 3? Minus 2? Yeah, so for any element, there's always 2 choices. You can add electrons or you can take electrons away. 6 valence electrons in sulfur, so we can take all those electrons away and make it plus 6, or we can add 2 to make it minus 2. What's probably more likely? Minus 2, right. So we're going to make the lithium ion as minus 2, 2 minus. Or the sulfide ion, sorry. All right, so we've got lithium and sulfide. If we want to write a formula for that compound, do we just put those 2 together and say LIS?
No.
Why not?
We have to do something with our charges.
Yeah, we have to do something to balance the charges. We can't have plus 1 and minus 2 because it has to equal 0 overall. How do we fix it?
Li2 is
Right, so we're going to add a second lithium to balance out that sulfide. And the overall formula then will be Li2S. Yes.
Why we not try minus 2?
Good question. Yeah, why aren't the charges in the formula? Once the formula is together, it's all neutral. So if you put a charge up there, it looks like the whole formula has the charge. We want the whole compound to be neutral. So we take those charges out when we put them together and write the final formula. Okay, let's try a tougher one. Aluminum chloride. If you don't have a periodic table with the names handy, aluminum is Al and chloride is Cl. So see if you can do this one on your own. Figure out the charges and then figure out how you would put this together to make a formula.
So I get this, but I don't understand how you get the charges from here. I know that briefly, column 1, 2, and 3 are positive, 1, 2, and 3.
Yep.
But I don't understand how
How you get the rest of them?
all the way down.
It's about thinking about those valence electrons in those buckets. So you got to fill up the bucket or empty the bucket. The numbers on the column give you the number of valence electrons. So you say, all right, well, let's take aluminum, for instance, number 13. That's in column 3. So that means it's got 3 electrons in its valence shell, 3 electrons in the bucket. the buckets want 8. So either we add 5 more electrons and make it -5, or we take those 3 out and make it +3. So in that case, we're going to take the 3 out because that's fewer electrons, and that's why it becomes +3. The rest, once you get past the fourth column's tricky because it could go either way because it's 4+ or 4-, and then it goes to minus as you go the next 2 columns. Yeah. All right, anybody feel good about the formula for aluminum chloride? Everybody get something?
Okay, we'll see. -2.
All right, so let's look at it. What'd you get for a charge for aluminum? +3, right? And what about chloride? -1. -1. It's got 7 valence electrons, so 1 more makes 8, so -1. All right, how do we bring those 2 ions into balance so that the overall compound is neutral? Right, more chloride. We need 2 more chloride. Right? What? Right, because we need 3. If we're going to have 3+ from the aluminum, we need 3- from the chlorine, from all the chlorides. So we can say that overall, these all together are 3-. Now we've got 3+, 3-. That works. The way we express that in a formula then is AlCl3. All right. Let's go one more step here. We'll stick with aluminum since we just did that one. We know that one. But this time we're going to pair it with oxide. Oxide is, oxygen. All right, same question. O from oxygen. Number 8, sorry. This one's you might run into a little trouble. See if you can work through the trouble. Something isn't going to work quite right here. But maybe you can figure it out. All right. We got aluminum, Al, and that's 3 plus again. And oxide, what's the charge on oxide? 2 minus. All right, so how are we going to bring these two into balance? Well, let's look at it. What did you say?
2AL and
Uh-huh.
3.
Right, so in this case, we can't just change one or the other. Because if you have 2 ALs, that's 6 plus, to the oxygen's 2 minus. If you have 2 oxides, that's 4 minus to 3 plus. So it doesn't work if you only change one. So you have to change both of them to find a common multiple. We take 2 of these to make 6 plus overall. And then we can make 6 minus from 3 oxides. See how the 2 aluminums make equal to 6, or the 3 oxides? That means that our formula will be Al2O3. Okay, one more, and then we'll move on. Oh. Someone's freaking out here. There we go. Try this one, magnesium nitride. Magnesium is, if you don't have the table with you, Mg. Nitride is the ion from nitrogen, N. So what would that compound look like? All right, you think you got this one? What do you get? Okay. Anybody else?
Can we
Yeah.
get the first ion negative?
No,
Only positive.
only positive. So in this case, magnesium is in the second column. That means 2 valence electrons, so it can lose those 2 valence electrons to become 2 plus. Nitrogen is in the fifth column, 5A, 5 valence electrons. So what would be the common charge of that ion? 3 minus, right? Yeah. So we have a similar situation as the last one, just backward, just reversed. We have a 2 and a 3, and the only way you can bring a 2 and a 3 into balance is to make both of them 6. So the magnesium gets tripled, and the nitrogen gets doubled. We put that all together, and we get Mg3N2. Good so far? All right, we're going to make one little change now. We're going to start talking about this big, messy middle area that we've been ignoring so far, the transition metals. That block in the middle is called the transition metals, and because those electrons are in d orbitals, which is a whole different kind of a thing that we haven't gotten into yet, we'll talk about that later in the semester, the electrons have different and less predictable behavior than the others. So we can't say nice things like titanium Ti is in column 4b, therefore this is the charge. It's not quite so simple. Those elements all have different possible charges. And they're known as I said, the transition metals. So that would be 3b to 2b. And they have variable charge. For instance, iron can be 2 plus, or it can be 3 plus. Copper can be 1 plus or 2 plus. Some of them have multiple different charges they can be, etc. So we're not going to memorize a bunch of charges of transition metals because they could be whatever. And that way, when we're naming them, we need more information. Like here, we said magnesium nitride. We can look up magnesium. We can look where it is in the periodic table, and we know it's got to be 2 plus. But if we said iron nitride, or iron chloride is more common, we wouldn't know. Is it iron? Is it the +2 iron, or is it the +3 iron? That's going to change everything. So when those things are named, we specify the charge with the ion right after it. So let me show you what that looks like. Instead of just saying iron chloride, we say iron 3 chloride or iron 2 chloride. Those are different compounds. There's older names for those as well that you might run into. They used to be called ferric chloride and ferrous chloride. We're not going to use those older names because they're not systematic, meaning you just have to remember what they were called. There's no way of saying this always works for everything. Whereas this way, this is what's used now, this always works for everything. So all of these ions will have a number in parentheses after them that tells you what the charge is. Notice that it does not tell you the little subscript number. It doesn't tell you the number that you put in the formula. It tells you the charge. So you still have to do the work that we did before, but you know the charge. Let me show you what that looks like. So iron 3 chloride tells us that the ion in question here is iron 3 plus. These are all going to be positive ions, by the way. Those transition metals don't commonly make negative ions. And our chloride ion is still -1. So how do we bring those two into balance?
We have to add 2 chloride.
Right, we're going to need a couple more chlorides. And that means that our formula for iron 3 chloride is FeCl3. It's tempting to want to put that 3 down by the iron because you read it as iron 3 chloride, so you want to put the 3 down here. But that's not correct. The 3 in the parentheses is the charge, and you still have to balance the ions out and figure out how to make a neutral compound. That means that iron 2 chloride is going to come from iron 2 plus and Cl minus. We'll need one more Cl minus to balance that and get FeCl2. The rest of the work is the same as what we just did, but that parentheses tells you the charge on the ion. So here, try a couple more of them. Try copper 1 sulfide and titanium 4 oxide. And if you don't know these names, if you don't have periodic table handy, copper is Cu, sulfide is S, titanium is Ti, and oxide is O. So see if you can find the charges and then put the compound together so that there is a neutral compound. All right, get some compounds. Feel good about it? Okay, let's look at it. What is the charge on copper going to be here? Yeah, just +1, because it tells us right in the name, copper 1 must be +1. And what about sulfide? -2. We've talked about that already. So. All right, so how do you put those two together?
We have to add one copper.
Like this? Yeah, we need 2 of those coppers so that it's overall +2 to balance out the -2. There's our compound. Okay, and what about the titanium 4 oxide? What's the charge on titanium? 4+ and 2-. Right, we're going to add an oxygen and get TiO2. Yeah.
For titanium, we can lose 40, but this will be minus and minus. It will not happen. Yeah.
Yeah, we can't figure out the charge of titanium from the periodic table, but we're told here this 4 tells us it must be +4. So this, when there is a number here, it's always plus and then number. Yeah. Okay, great. I guess there's room here. So that is ionic compounds, finding these charges, putting them together, and trying to balance it out. We'll try one more, and then we will call it a day. Ruthenium 3 oxide. Ruthenium is Ru. Oxide is O. So see if you can put those two together. And then tomorrow we have lab, and Thursday we'll talk about going the other way, where we actually come up with the names from the compound. So please bring a periodic table that has names, or book, lab manual, all that stuff. Anything that has names on it, so you can look at that on Thursday. All right, got something? Charge on ruthenium is 3+. Charge on oxide is 2-. So
We have to add one ruthenium and 2 oxides.
yeah, this is just like the aluminum one before, because we got to get 6+ and 6-. So that compound then will be Ru2O3. All right, keep working on this. Being able to write formulas from names is going to be really important moving forward, because we'll use that when we talk about reactions and when we talk about other types of calculations. It's going to be something we do for the rest of the semester. So it looks like we've got a good start. Keep working on it, and we'll continue on Thursday. Okay, we'll stop there. See you in lab tomorrow, 12:30 regular time upstairs.